Good morning, everyone, and welcome. I'm Dr. S.K. Singh, and today I will be guiding you through the calibration of a specific optical rotation instrument. This is an essential process to ensure accurate measurements in optical activity studies. Over the course of this presentation, we'll cover the fundamental concepts, the calibration procedure, and some practical tips to maintain precision. I'm excited to share this knowledge with you, so let's get started. Let's start by looking at some key parameters that influence optical rotation measurements. These include wavelength, temperature, the cylinder path length, and concentration. Each of these factors plays a critical role in ensuring accurate and reproducible results. Wavelength refers to the specific light used in the measurement, and selecting the correct wavelength is essential because optical rotation is wavelength dependent. Temperature is another vital parameter. Even small changes can affect the rotation angle, so maintaining a stable temperature is crucial for consistency. The cylinder path length, or the length of the tube through which the light passes, directly impacts the measured optical rotation. Longer path lengths typically increase the rotation effect. And then there's concentration, which influences how much the substance affects the polarized light. Higher concentrations generally lead to larger rotations, but it's important to measure and control this carefully. Now, moving on to some foundational concepts. Today, we'll introduce what specific optical rotation, or SOR, actually is. It's a standardized way to express how much a substance rotates polarized light under specific conditions. We'll also demonstrate the calibration procedure for our optical rotation instrument, the polarimeter. Proper calibration is key to obtaining accurate, reliable measurements. Finally, we'll make sure our approach aligns with regulatory standards, specifically USB guidelines, ICH Q2, R1, and other expectations from regulatory bodies. This ensures our measurements are not only precise, but also compliant for quality control and documentation. Now, let's briefly cover some key definitions. Optical rotation, denoted as alpha, is the effect of a substance to rotate the plane of polarized light as it passes through. Specific rotation, or alpha, is this optical rotation value normalized for concentration and path length, allowing us to compare different samples and conditions more effectively. Understanding these parameters and definitions helps us ensure our measurements are accurate, consistent, and aligned with regulatory expectations. Let's take a closer look at the regulatory requirements that govern our analytical methods. First, we refer to the USB General chapters, which provide essential guidelines for ensuring quality and consistency. For example, 781 covers optical rotation, a critical parameter in many pharmaceutical analyses, while 1058 focuses on analytical instrument qualification, or AIQ, which helps us confirm that our instruments are performing correctly. Moving on to regulatory expectations, it's important to remember that calibration must always be documented. This creates a clear record of instrument performance over time. Additionally, instruments should be validated before they're put into use to ensure they meet the necessary performance criteria right from the start. Traceability is also a key point. Our measurements need to be traceable back to reference standards. This ensures accuracy and consistency, aligning with regulatory standards and maintaining the integrity of our data. Connecting all these points to our broader theme, following these regulatory requirements helps us keep our processes compliant, reliable, and scientifically sound. It's all about building confidence in our results and maintaining the highest quality standards. Let's take a closer look at the equation for specific rotation. This equation is fundamental in understanding how chiral compounds interact with polarized light. Essentially, it allows us to quantify how much a substance can rotate the plane of polarized light, which is key in stereochemistry and optical activity studies. The equation itself relates the observed rotation to factors like concentration and path length, giving us a standardized way to compare different substances. By mastering this equation, we can better interpret experimental data and identify various compounds based on their optical properties. This ties into the overall theme of understanding molecular structure through optical techniques, which is a powerful tool in chemistry. Let's talk about calibration standards. First, we have the primary reference standard, which in this case is sucrose, specifically the USB reference standard. This means it's a well-characterized material that we rely on for its known properties. For sucrose, the known specific rotation at 20 degrees Celsius and the D line is plus 66.5 degrees, according to USB. This value is essential because it serves as the benchmark for our measurements. Next, we have the secondary standard. These are solutions prepared from the primary standard. Think of them as intermediates that make routine checks more practical. Instead of always using the primary standard directly, we prepare these secondary standards to verify that our instruments are functioning correctly over time. They help ensure consistency and accuracy in our measurements without the need to handle the primary standard repeatedly. So, to tie it all together, calibration standards are fundamental for accurate optical rotation measurements. The primary standard provides the definitive reference point, while the secondary standards are practical tools for regular verification. This process helps us maintain precision and confidence in our analytical results throughout the testing process. Now, let's talk about how we prepare our calibration solution. We start with a standard, which in this case is USB sucrose. The reference value we're aiming for is a temperature of plus 66.5 degrees Celsius at 20 degrees Celsius, using the sodium D line at 589 nanometers. This helps us ensure consistency and accuracy in our measurements. For the preparation, we weigh out 26.65 grams of sucrose. Then, we dissolve that in enough water to make a total volume of 100 milliliters. This results in a concentration of approximately 0.2665 grams per milliliter. We'll be using a 1 decimeter path length cell for our measurements, which is standard for spectroscopic calibration. It's important to get this preparation right because it forms the basis of our calibration curve, ensuring that our subsequent measurements are precise and reliable. By understanding and carefully preparing this solution, we set a solid foundation for accurate temperature and spectral analysis. Let's talk about calculation. First, it's important to understand that calculation is at the core of many of the decisions we're making. It helps us quantify our options and predict outcomes. When we perform calculations, we're essentially translating data into meaningful insights. This allows us to compare different scenarios objectively. Remember, accurate calculations depend on reliable data, so always double-check your figures. Most importantly, calculations connect back to our overall goal of making informed, strategic choices. They serve as the foundation for everything from budgeting to forecasting and beyond. So, mastering calculation skills is key to driving successful outcomes in our projects. Let's talk about the acceptance criteria first. When we're measuring optical rotation, we expect the specific rotation to be within plus or minus 0.5%, or as specified by our laboratory SOP or USB tolerance. It's crucial that the temperature stays within the defined limits because temperature fluctuations can affect the rotation measurement. Usually, we set the wavelength at 589 nanometers, which is standard for these measurements. Now, moving on to the calibration procedure. The first step is to warm up your instrument according to the SOP, ensuring it's ready for accurate readings. Next, check the temperature of the environment. USB requires it to be around 20 degrees Celsius, plus or minus 0.5 degrees, or as specified for your test. Then, prepare your standard solution, like a sucrose solution, which serves as a reference. Insert the sample cell, zero the instrument, and record the observed rotation. After that, you'll compute the specific rotation using the observed data. It's important to compare this value with the known reference value to verify the instrument's accuracy. Finally, document all your results carefully, including whether they meet the acceptance criteria. This process ensures the reliability and consistency of your measurements, which is vital for quality control and overall product integrity. Let's take a look at some common errors and troubleshooting tips. When working through any process, it's important to recognize that mistakes can happen, but they can often be quickly resolved. One key point is to stay patient and methodical. This helps you pinpoint the source of the problem. For example, if something isn't functioning as expected, double-check your connections or settings first. Sometimes, a simple reset or restart can clear up issues. Also, keep an eye out for common misconfigurations or overlooked steps, as these are frequent culprits. Remember, troubleshooting is about systematically eliminating possibilities until you find the root cause. By understanding these common errors and having a troubleshooting plan, you'll be better equipped to handle challenges efficiently. This ties back to our overall goal of ensuring smooth and reliable operation, even when issues arise. Let's take a moment to discuss the importance of documentation and records in the process. First, it's essential to include the standard identity and lot number for each batch. This helps us track exactly what was produced and when. Calculations are also critical. They verify that all parameters meet the required specifications. Next, we need to record the instrument ID and configuration. This ensures that the equipment used is identified properly and set up correctly for each run. Temperature logs are another key element. They provide a continuous record of the conditions during processing, which is vital for quality control. Acceptance status is also documented, indicating whether the batch passed or failed the criteria. And of course, the operator's signature and date are necessary to authenticate the records and confirm accountability. Finally, it's important to remember that these records must be retained for the specified period, as dictated by regulatory requirements and our standard operating procedures. This ensures that we can review and verify our processes at any future point if needed. All these elements together form a comprehensive record that supports quality, compliance, and traceability throughout the process. Let's wrap up with some key takeaways. First, the importance of specific rotation calibration cannot be overstated when it comes to ensuring compliance. Accurate calibration is the foundation for reliable measurements. Next, it's essential to follow the USP 781 and 1058 guidelines, as they provide the standardized procedures to maintain consistency and quality. Proper preparation, accurate measurements, and thorough documentation are also critical steps in this process. They help us ensure data integrity and traceability. And finally, the examples we've discussed today confirm that adhering to these practices leads to acceptable and compliant results. Keeping these points in mind will help us maintain high standards in our work. For further support, please feel free to contact us. We're here to help with any questions or additional guidance you might need. Thank you so much for your attention and engagement throughout this presentation. If anything comes up after today, don't hesitate to reach out. Your success is our priority, and we're glad to assist you whenever needed. Once again, thank you for being part of this session.